Dear student, today I discuss about the properties of the transition element. In the previous class or lecture, I had discussed about the what is transition element, why it is so called, its electronic configuration, and in the next lecture what is the radius and the how radius of the transition element varies along the period and downwards the group. Giving in the general concept, the radius of atom in general in periodic table from left to right, but its radius decreases, and in the group radius increases, but in the infinite, and we already have seen the cases. Now today, because radius is related with that, ionization energy is related with that of the radius, so we have the concept of the radius needed priorly. That's why radius variation was discussed in the previous classes. And doing this lecture, and we have the concept that is if we move in a period, general concept, period, general concept, general concept, if move in the period, ionization energy or ionization enthalpy increases. And if we move in a group, that is ionization energy decreases, generally in the S and P block element, general concept. So we have the ionization energy is inversely proportional to radius, but ionization energy, this is also Z effective. Z effective. This ionization energy is related with the radius. If radius increases, ionization energy decreases. And if effective nuclear charge increases, the force of attraction between the valence electron and the nucleus increases, needs more energy to remove the outermost electron. That's why its ionization energy in that situation also increases. Now, out of these two factors, ionization energy also depends upon, that is, electronic configuration. Electronic configuration. Electronic configuration. And another factor that will depends upon, that is the screening effect or the shielding effect. SCREENING, screening effect. Screening effect. But in chemistry, there are so many exceptions. Likewise, in the ionization energy, there are so many exceptions in addition to the normal trend. So the first three element, if we first 3D series, 3D, that is start from scandium to zinc. Now scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, and zinc. This is the first transition series. This is called third transition series. Now the second is yttrium, zirconium, nickel, palladium, Ag, Cd, this is Cd. Now the here third transition series, this is 4D, and this is second, and this is third transition series, this is called 5D series. This is called 5D series. So we write here, this is lanthanum, and this is 57, this is 39, right? And this is 21. Okay. Sorry. This is 22, 40, and this is here aphelium. This one, this is aphelium. Here there is a lanthanides, and this is actinides. This is 89. So what we see, and here is a nickel, palladium, platinum, and this is Ag, Au, and this is Hg. So what is the general trend or variation of ionization energy? Variation of ionization energy along the period. Along period in 3D series. First we talk about the 3D series. So when we move in the 3D series, that is from scandium to zinc, we see that the radius, due to the screening effect, the radius increases, this is decreases slowly. That's why ionization energy increases slowly. So from left to right in the period, ionization energy increases slowly. As radius decreases slowly. And why the radius decreases, there is two counter effect. In the beginning, the screening effect is less. There is atomic number 21, 22, 4, 5, 6, 7, 8, 29, 29 and 30. This is. So in the beginning, screening effect is less, and as soon as the electron enters in the d orbital, screening effect increases, and the effective nuclear charge Z effective is more than that of what? This is the screening effect. Screening effect in the beginning. So the radius, due to the increased number of proton, the outermost electron is increases, and that's why the radius decreases slowly. And in the mid, it is almost the same. Means the increase in nuclear charge is counterbalanced by screening effect. Although the almost the same, means the radius is not equally equal, means almost same. So radius decreases slowly. This is due to, and the ionization increases slowly. So and when we come at the end of the transition series, the ionization energy, that is high. That is at the end of the slowly, that's why ionization, and at the end, that is ionization energy high. This is. So why zinc have the high ionization energy? Because there is electron is, the d orbital is completely filled. Now due to the filled configuration, it is a stable one. To remove the electron, it needs very high energy, and that's why its ionization energy is very high. Now the second point, the increase of ionization energy from left to right in the transition series is not very regular. Sometimes it increases, little bit it decreases, and at the end it is increases. At the end it is increases. So, while there is a irregular trend in the variation of ionization energy, this irregular trend, this irregular trend is due to the removal of electron from the S and the D subcell that alters the energy of the orbitals. This is a s orbital and d orbital. That's why there is a irregular trend in the energy. Now we discuss. Now, so we take a case. Suppose we take the radius. What we see, radius of you compare the radius of that is copper and radius of zinc. So radius of zinc is smaller or higher than that of copper. So it is at the end, its radius is. What is about the ionization energy? If we apply the concept here, if ionization radius is high, ionization energy will be low. But we say the ionization energy is also high. This its ionization energy, that is zinc, is higher than that of this is the copper. Again question arises, why the ionization energy of zinc is higher than that of copper? So it is at the end. So if we write that will also be, it not only depends upon the radius, because the radius of the zinc is higher, so its ionization energy should be lower as per general concept. So but when we see the numerical value or calculated data, we say the ionization energy of the first ionization energy of the zinc is higher than that of the copper. Why? It is due to the electronic configuration. So the another factor was that is electronic configuration. If we look at the electronic configuration, 3d10 and this is 4s2, and we looked at the configuration, this is 3d10 and this is 4s1. So to remove the first electron, here if we want to remove the electron, here from a stable configuration, because these are completely filled, ds is also completely filled, so it is a stable configuration. So if we remove electron, it needs more energy to form Zn plus Zn plus, that it will have configuration 3d10 and 4s1. Now from here, if we remove one electron, it forms copper, and this is 3d10. So the first ionization energy, although radius of zinc is more than that of copper, ionization energy of zinc should be less, but its ionization energy follow the same trend as the radius follow. Why is it so? Due to the stable configuration. It needs very high energy configuration and needs very high energy. Needs high energy. This is it. So if it needs very high energy, it means ionization energy of zinc is very high than that of the copper. If we talk about the first ionization energy, so we write here the ionization energy first of zinc is higher than that of copper. If we talk about the second ionization energy, copper plus and zinc plus, and this have configuration 3d10, Again, this will have configuration. This is a 3D10 and the 4s1. Again, to remove needs energy, this is stable, and this is have when we remove the one electron to form copper 2 plus ion, remove one electron to form Zn2 plus ion. So this one is stable. This copper 3D10 and this will have the 4, that is 4s1. Again, to remove the second electron, it needs a high energy. Needs high energy. High energy. That's why we say that is the ionization energy second of what? This is the copper is greater than that of the zinc. So what we observed in the period, if we go in a period from left to right, we say the ionization energy increases, but the increases very slowly, and at the end energy increases very slowly, and zinc will have the highest energy in the each period. Similarly happens in the second and the 5 transition series. If we talk about the 5D series, 5D series. Now, if we talk about before going to that, right? 5D series. 5D series. This 5D series is said the third transition series have highest ionization energy than that of, this is 5D series, have higher ionization energy than that of 3D and 4D series. 4D series, right? So we talk about here, when we come from zirconium to hafnium, it is size, what here? That is in the group radius increases, ionization energy decreases. This titanium will have higher ionization energy than that of this zirconium. Now, when we come upon zirconium to hafnium, then what will happen? The its radius is almost the same. Radius is almost same. This radius is almost same. The hafnium is same. So, if radius is same, the ionization energy should be same. But no, this ionization energy is never same. And why it is not same? If radius, we say is the radius, this is the radius. If radius are almost equal, the ionization energy should be equal in all the states, right? But it is not found to be the ionization energy of the 5D series, that is hafnium, is higher than that of the that is the zirconium. Because in 5D series, the electron enter into the F subcell. Again, F subcell, and F subcell is much more diffused. They do not send the nucleus effectively, that it has the poor sending. Nuclear charge increases, so attractions of the valence electron towards the nucleus increases. That's why ionization energy increases. That's why the 5D series will have higher ionization energy than that of the 3D and the 4D series due to, single word, due to lengthenoid contraction. Lengthenoid contraction. So, what is lengthenoid contraction? We know it very well. Okay. In the after lengthenum, just it happens on lengthenum, then it is called the from start from hafnium, so it is called the lengthenoid contraction. Means in lengthenoid contraction, I had already explained it. Okay, in lengthenoid contraction, the electron enter into the 4F subcell. Here we 4F14, right? So F subcell is much more diffused. Diffused means they are away from the nucleus. Nuclear charge increases. This outermost electron, suppose we consider here the nucleus. Suppose here we consider the nucleus. If it is near the nucleus electron, then it is effectively sealed. This nucleus is away here, here, here. So this will not effectively seal. Now this is the outer electron. Nuclear charge here increases. Nuclear charge here increases. So it will be attracted. If the attraction is more, then needs more energy to remove the electron. So all this is called the lengthenite contraction. So one word we say, if 5D series have the higher ionization energy than that of the 3D and 4D series, then we say that is it is due to the lengthenite contraction. So if we do not say from here to here, that is ionization energy, this zirconium to hafnium will remain the same as its radius is same, it will be wrong. This hafnium will have higher energy than that of the zirconium, although its radius is almost same, because of the lengthenite contraction, or the electron enters into the F subshell, and this F subshell is much more diffuse, means it has poor shell length, so the increased nuclear charge attract the electron, so its ionization energy increases. Now, so again we take another case, how it varies the ionization energy. Suppose we take here, that is the case is zinc, that is copper, this is copper, right? And this is Az, and we take E, right? So this is 3D, this is 4D, and this is 5D. What happened? On coming down the groove, the ionization energy decreases. So this copper will have the high ionization energy, right? But as discussed, the 5D will have the higher ionization energy, so this gold will have the higher ionization energy than that of this. So the order comes to be, if we write in a way, arranged way, this is Ag, then followed by copper, and then this is Az. So it is written as 5D, then it is 3D, then it is 4D. So it is not general. This is the exceptional in some cases. Similarly, it will follow, that is Hg, and similarly cadmium, and similarly that is the zinc. But if you write about tell about the chromium, that is molybdenum and tungsten. So in that cases, the order of ionization energy, this is tungsten, then molybdenum, then chromium. Then we say 5D, then it is 4D, and then it is 3D. So these are so many exceptions are there. So what is the reason of the exception? And this is explained. Sometimes we should go to the that is lengthenite contraction, and the general order in a period, if it is said that out of 3D, 4D and 5D, why 5D series is the highest ionization energy, this is also due to the lengthenite contraction. Now we take the another case, like this another case we take. Suppose we take this is chromium and manganese. There are so many exceptional cases, we should discuss it. This is chromium and manganese. So chromium is 24 and this manganese is 25. And now we are able to write the electronic configuration. This is 35 and this is 4s1. And this is also argon, and this is 35 and this is 4s2. So which will have the first ionization energy will be moved as our general concept. We move from left to right, that is radius decreases slowly, ionization energy increases slowly. So first ionization energy, if we talk about the first ionization energy, then whose first ionization energy will be more and why? Now this is 3d5, this is all a half filled, full filled. So to remove the electron, and this is half filled and this is half filled. So this is more stable configuration. Again, electronic configuration play a vital role, and this is also the stable configuration, not stable configuration. So what will happen? It needs more energy. Needs more energy. More energy to remove first electron and to form Mn plus. Now this Mn plus 3d5 and 4h1. Now to remove here from the first electron, remove first electron, sign is this, like this is chromium plus and this is 3d5, right? So the first ionization energy in this case, now we remove it all. So see, in this case what will happen? This, here it is a stable configuration. So first ionization energy of which this is Mn is greater than that of chromium. If we talk the ionization energy second की बात करें यदि हम लोग here ionization energy second. So what will happen? This chromium Cr plus and Mn plus. So electronic configuration depends upon this is the ionization energy depends upon electronic configuration. This is the important factor. This is 4h1. So it is a stable, it is not stable. So to remove the second electron to form chromium 2 plus ion, then it will have configuration 3d4. 3d4. Now it needs more energy. And its configuration Mn2 plus, that is remove electron. So it needs less energy. Is it clear? This needs less energy. So electronic configuration of transition metal depends upon follow the general trend, and some depends upon the electronic configuration. Just you see the case of the copper and zinc, and you have seen the case of chromium and manganese, and then the second ionization energy of chromium will be greater than that of the manganese. Now, anyway, if we have the concept, then we can explain about the third ionization energy. Now we talk about the third ionization energy. If we talk about the third ionization energy, this is chromium 2 plus and this is Mn2 plus. This chromium 2 plus have 3d4 and this will have 3d5. So we have the concept which one is more stable, that is d4 or d5, because it is completely half filled. So this one is stable and this is not stable. So it needs high energy. So if it needs a high energy, means its ionization energy third will be to remove electron and form the Mn3 plus ion, and it will form the chromium 3 plus ion and remove electron. So the third ionization energy of this will be very high. So if we talk about the ionization energy third, then the ionization energy third of manganese is greater, that is chromium will be less than that of manganese. So the general concept is that in the transition element, if we move from left to right, the radius decreases slowly due to lengthenite contraction. That's why ionization energy increases slowly, and zinc will have the highest ionization energy in the third series. It is due to the stable configuration, right? Now, the trend of ionization energy in the first transition series is not very regular, because of the removal of the electron from the n minus 1d and ns subset alters the energy of the orbital. That's why its trend is not very regular. Now, if we talk about the variation of ionization energy, if we come down the group, then 3D will have higher ionization energy than the 4D because of this one, and the third and the fourth transition series. If we come on the 4D, second and the third transition series, that is 4D and 5D, if we come down in the group, radius increases and ionization energy decreases. But it happens, but it does not happen. That is 5D transition series have the highest ionization energy than that of the 4D and the 3D series. Why is it so? Due to the lengthenite contraction. Because after lengthenum, hafnium is there. There are 14 elements. So in hafnium, the electron enters into the F subset, which is much more diffused, not shield the electron effectively. Nuclear charge increases, so the increased nuclear charge pull the electron towards itself, so its ionization energy क्या हो जाता है? Due to the strong, its ionization energy increases. That's 5D series have the highest ionization energy among the 3 series. It is due to the lengthenite contraction. So we have seen the order for the copper, zinc, and this what should be the order, and this is in some time we don't say the 5D, then 4D, then 3D, and there are so many exceptions. Electronic configuration, that ionization energy depends upon the electronic configuration and the stability of the orbital, that is electronic configuration and its stability. So I discussed the so many cases by taking it, this can be. And in general, the S block element will have lower energy, ionization energy, then D block element, and P block element will have the higher ionization energy. So this is the concept about that is ionization energy, and in next lecture we discuss about the that is electrode potential and its variation. Thank you.